So hello guys, welcome to my channel. Today in this video we will discuss about today's Leetcode POTD minimum height trees. Okay, so my name is Sushil Dey. Let's move towards the problem. So at first let's read the problem statement here. So what is given here? A tree is an undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without simple cycles is a tree. So everyone we everyone know that tree is basically a acyclic graph, right? So there is no cycle in between. That means if there are n nodes in our tree, then the number of edges must be n minus 1. Okay, if there are n nodes, then the number of edges must be n minus 1 in case of tree. Okay, so then given a tree of n nodes labeled from 0 to n minus 1 and an array n minus 1 edges where edges I is ai comma bi, where ai and bi basically represents the nodes. Okay, in between the edge is present. You can choose any node of the tree as the root. When you select the node x as the root, the result tree has height h. Among all possible rooted trees, those with the minimum height mean h are called minimum height trees. Okay, that means there are basically 0 to n minus 1 nodes. Okay, that is total n number of nodes is given, and you can choose any node as the root node, and the height from that particular node must be minimum. And what you have to return? You have to return a list of all MHT root levels, and you can return the answer in any order. Okay, and what is height? A height of a rooted tree is basically the number of edges on the longest downward path between the root and the leaf. So for example, let's draw a tree here. So if we consider 1 as our root node, then what will be the height? The height will be 2, right, in this direction, because the length of the maximum path, that is 1 2 3 to 4, is basically 2. So here the height will be 2 if we consider this particular node. And what we have to think about the nodes from which the height is minimum. Okay, and these minimum height trees, we have to return the list of these minimum height trees root levels. So just hold on and let's think a little bit that these MHTs, isn't it the nodes that is basically present at the center? Because it is the center nodes from which the distance of the leaf nodes are equal. Okay, because from the center nodes, for example, the center nodes is 2. From the center nodes, the left leaf node and the right leaf node has equal distance. So only for the center node the height can be minimum, right? We can visualize this in this way, that the center node is basically presented in this direction, right, and its leaf node is basically spread from outwards direction. Okay, and from the center node, as the leaf nodes are equidistant, that means here the distance is almost distributed, and in that case the height can only be minimum, right? So we have to think about the center nodes. Okay, so this is our first observation, that we have to think about the center nodes, because from which the height can only be minimum, right? So about the center nodes. Now what can be the possible number of MHTs here? So to answer this particular question, let's see for few examples here. So let's consider this particular tree. So here, what is the number of centered nodes? The number of centered nodes is 2 here, that is 1 and 2. And if you choose any of these nodes, the height of the tree will be 1. If you choose this node, then the height is 1, and if you choose this particular node, the height will also be 1. Okay, so here the possible two nodes is 1 and 2. Then take another example, that is 1 2 3. Now here the number of center nodes is 1, right, that is 2 is the center node here. And if you choose this particular node, the height of the tree is 1. Okay, that is one direction from right and from left. So here the number of center nodes is basically 1, and that is the node 2. Okay, so if we observe carefully, the number of center nodes in any tree, okay, in any given tree, the number of center nodes can be either 1 or 2. It can't be 3, right? Because if it is 3, then the center node of these particular 3 nodes will be our new center, right? So the number of center nodes can either be 1 or 2. So now how we can determine the center nodes? So to determine the center nodes, we have to visualize this problem in this way, that all the lists basically form a outer shell. Okay, and if we pop these particular leaf nodes and check for the next leaf nodes, this will be outwards. And if we try to popping the leaf nodes up and until the remaining number of nodes is greater than 2, will eventually move towards the center, right? This would be much more clear if we take an example. Let's see, a tree is given 1 3. In this manner a particular tree is given here. Okay, so we can also write the tree in this way, that is 1, here there is 2 nodes, 2 and 3, then 2 is connected with 4 and 5, so 2 is connected with 4 and 5, and 3 is connected with 6 and 7. So initially the leaf nodes are these particular 4 nodes, right? These particular 4 nodes are initially the leaf nodes. So what we will do at first, we will pop all these leaf nodes. Okay, and after popping these 4 leaf nodes, we will check the next leaf nodes. So after popping these 4 leaf nodes, let's erase this. So after popping these 4 leaf nodes, the new leaf nodes will be these particular 2 nodes, right? That is 3 and 2. So if we pop these particular 2 nodes, eventually we will reach towards the center. Okay, so for any tree, for any given tree, if we do in this manner, that at first for any given tree, for example a tree is given in this way, at first we'll pop all the leaf nodes. Okay, then after popping this, we will check for the next leaf nodes, and we'll do that up until the number of remaining nodes, the number of remaining nodes is greater than 2, right? Because the number of center nodes is basically less than equal to 2, so minimum less than equal to 2 number of nodes must be present at last. So we'll try to pop all the leaf nodes, okay, up until the number of remaining nodes is greater than 2. So in this way we can reach towards this center, and finally can determine the MHTs. Okay, the MHT nodes, the MHTs node. So let's move towards the code, then the concept will be much more clear. So at first we will declare our adjacency list, right? We have to declare our adjacency list, that is basically a 2D vector G of length n, because there are total n nodes from 0 to n minus 1. Okay, and here we have also write a base condition here. If the number of nodes is 1, then we will simply return 0. Okay, because if there are only one node present in the tree, then there is no point of doing further process. Okay, we can simply return this particular node. One node means there are only node with id 0. Okay, so there are no other nodes, so this is the only node that is our MHT's root, and here the height is 0, sorry, here the height is 0, because the root node and the leaf node both are same. So in that case we will just return 0. Okay, if the number of nodes is 1. So here we will write a base condition that if the number of nodes is 1, we will simply return 0. Okay, then we will store the nodes in our adjacency list. Auto page, yes. So here we will run a for each loop, and we will store the value of two age into variable u and v. Okay, so int u equal to age 0 and int v equal to age 1. So this u and v basically signify the two nodes among which the particular age is present. Okay, then we will store that node in our adjacency list, that is g of u dot pushback v, and as this is bidirectional, so we will also push u as the neighbor of v. Okay, as it is undirected, so we can move in both direction from u to v or from v to u. And we also have to declare a vector degree here, vector named degree, in which we store the degree of all the nodes. Okay, and we will initialize all the value with 0. So here we will store the degree of all the nodes as there are a particular age between u and v, so both u and v will increment both the degree of both u and v by 1. Okay, so here degree of both u and v must be incremented by 1 as there is an age between u and v. Next we declare a queue, and what we will do, we will basically store all the leaf nodes inside our queue, right? And what are the leaf nodes? The leaf node are basically those nodes which have degree 1. Okay, because this is a property of a leaf node. A leaf node must have degree 1, right? So we will simply run a loop from 0 to n and check for the nodes those have degree of 1. Okay, and we will eventually store those nodes inside our queue. So storing all the leaf nodes inside our queue. Okay, now we will declare a variable named remaining nodes, that will store the number of nodes that is remaining after popping the leaf nodes. Okay, so this must be initialized with n because initially there are total n nodes, and with each popping of the nodes we will updating this particular variable, and we will run the loop up until the number of remaining nodes is greater than 2, right? The number of remaining node must be greater than 2. So here at first we will store the size of the queue in a variable t. Okay, and this is basically the number of leaf nodes in the current state of the tree. Okay, so we will store that in t, and we will subtract it from our remaining nodes, as we will pop all the t number of nodes in our next steps. So we will subtract this from our remaining nodes, and then we will run a loop from 0 to t, within which we will pop all the t nodes, that is we will pop all the leaf nodes, and after popping those t number of leaf nodes, we will get a new state of the tree, and we will again run the same algorithm on that tree. We will again check the new leaf nodes, and will eventually pop that up until the number of remaining nodes is greater than 2. Okay, so here at first we will take the front element of the queue and then pop that particular element. Now we will check the neighboring nodes of this particular temp node, right? We will check for the neighboring nodes of this particular temp node. So here, as I am popping the temp node, right, I am deleting the temp node, So all the neighboring nodes have so the degree of all the neighboring nodes must be decremented by 1, right? Because we are deleting this particular node, so the degree of all its neighboring node must be decremented by 1, right? So we will decrease the degree of its neighboring node by 1, and now we will check whether the degree of this particular neighboring node is 1 or not. If this is 1, that means after popping this particular node, this neighbor node will be the new leaf node, right? So we will eventually push that new leaf node in our queue. So here, if the degree of new leaf node, that is the neighbor node, if this degree becomes 1 after popping this particular temp node, then we will push that in our queue. Okay, and after running this loop, we will store the remaining nodes that can be either the number of nodes can be either 1 or 2. We will store that remaining nodes in our answer vector. Okay, and those are basically the center nodes. So we will simply make the queue empty and pushing the remaining nodes of the queue in our answer vector. And finally we will return the answer. So let's run the code. So here the test case has been passed. So now let's submit it. So here, as we are doing BFS traversal, so the time complexity is basically order of n plus e, where n is basically the number of nodes and e is basically the number of edges. Okay, just simple BFS traversal in a typical graph. The time complexity is same, that is big of n plus e, and the space complexity is big O n, where n is basically number of nodes. Okay, so that's all. If you understand the solution properly, then like and subscribe to my channel, and see you in the next video.